So this is brand new stuff.
I love everything.
Okay, hold on, let me check.
Okay. That's all.
Yes, yeah.
It's not pure red.
Okay,
There's a caterpillar.
here we go. So, let's go back to the simple circuit. We got voltage, we've got resistance, and we've got current. Okay, and we've got our Ohm's law equation that controls it all. R equals V over I. Okay, but what if I wanted to add more resistors? Okay, so now we're talking about multi-resistor circuits and how they work. Okay, now there's two ways that I can add things in a circuit. There's a series connection and a parallel connection. Okay, we might have mentioned last class that whenever we're measuring current, we have to use an ammeter, and an ammeter must be connected in series. So let's add some resistors in series. So first I'm going to start with 1. Now in order to add in series, I've got to break apart the circuit. Okay? And then I have to add it in line with all of the other things. So like this is resistor 1, this is resistor 2. If I wanted to add a third one, just for kicks, you know, I'm going to have to break that circuit. If these were light bulbs, they would go out at this point. Okay? Then I'm going to add in another piece. Okay? So this is a series circuit. Notice that there's still only one loop. Okay? One loop means one current. So there are rules, and those rules kind of talk about, or not kind of, they do talk about the three things in our Ohm's law equation. So we've got a current rule, a voltage rule, and a resistance rule. Thankfully, they're all on your IB equation sheet. And they even tell you series versus parallel. Easy peasy, okay? So, like I just mentioned, because there's only one loop, there's only one path for the current to flow, and therefore only one current. Doesn't matter where I measure it, I can measure it here, or here, or here, or here, or here, or here, or here. I'm not going to always get the same current regardless of where I measure it in the circuit. So, if I were to, just to make sure things are clear, okay, if I measure the current right out of the battery before we reach any of the devices, okay, I'm going to call that I. That's going to be the current that flows through the whole circuit.
I hope you know that it's not dead.
And then if I can measure the current flowing through each branch, like let's say that the current that flows through R1, I'm going to call that I1. And the current that flows through R2, I'm going to call that I2. And the current that flows through R3, I'm going to call that I3. Yes, there we go. So, once again, the rule says that the currents are all the same. So the current that flows through the whole circuit, I, is going to be equal to all of the other currents. So I1 is equal to I2 is equal to I3 is equal to the current in the whole circuit because the current is the same in all parts of a series circuit. All right, very good. Now, next one, let's jump down to the resistance. So the resistance of a series circuit, that RS, well, we're just going to add together the resistors, okay? Easy peasy. R1 plus R2 plus however many we have, okay? Now, the voltage. So I've got the voltage of my battery. That's going to be the voltage of the source, or the source of the power here. Although power is really a misnomer because whatever. But if I were to measure the voltage across each piece, I would have to use a voltmeter, and a voltmeter must be connected in parallel. Okay, so the parallel connection, if I were to connect a voltmeter up here, I would have to get my voltmeter and put it right next to the thing that I want to measure over, and I'm going to take my wires and attach it before the item and after the item. Notice that it makes a new loop. That's a parallel connection. Okay, so I'm going to do that same thing with R1. I'm going to measure it over R2. I'm going to measure it over R3, and I should get 3 different voltages, like V1, we got V2, and V3. So our voltage rule for a series circuit is the voltage of the source is going to be equal to all of the voltage drops that come after it. So V1 plus V2, however many we have. These are our series rules, which again are listed for you just like that on your equation sheet. So we don't have to know them by heart, but we do need to know how to use them. The voltage is kind of like this, okay? I like to think of like the battery as like a voltage elevator. Like it brings up the charges, okay? And then as it goes around the circuit, as it goes across each resistor, it falls a particular potential difference or a different voltage. So V1, and then maybe V2 is bigger, and then maybe V3 is smaller. But all of the individual drops have to equal the voltage of the source, okay? All right, so now let's do a sample problem with the series circuit, okay? Here we go. So I'm going to leave those up there. I'm going to write a simple circuit here. Let's say that we've got a voltage of, let's say, 8 volts, okay? And let's keep it easy. Let's say that we've got a resistance of, let's say, 5 ohms. And this is going to be, let's say 9 ohms, okay? So we've got 2 resistors in series. Notice there's just one loop, that's a series connection. So there's all sorts of things that we can solve for here. One of them is, well, I want to know what's the total resistance of the circuit, okay? Also, what's the total current in the circuit? And then I'm going to look for the pieces, the small pieces too. What's the current that flows through the 5? And what's the current that flows through the 9? As well as, what's the voltage drop across the 5? And what's the voltage drop across the 9? Okay, so we're going to go through using these rules and our nifty Ohm's law that we talked about at the beginning of class, and we're going to we're going to calculate all of these different things. All right, here we go. First up, let's take a look at our resistance. So what's the total resistance of the circuit? 14. Yeah, you just add them up. Easy peasy, right? 14 ohms. There we go. All right, next. So this is the total current in the circuit. So I want to know, or I'm going to have to use my Ohm's law equation, solve for I. All right, so I is going to be equal to V over R as we switch things around, algebra stuff, okay? So now, the cool thing about Ohm's law is I can use it for the circuit as a whole or for each individual piece. It works both ways. It works big, it works small, okay? So when it works big, so this is going to be the current through the whole circuit, so that has to be the voltage of the whole circuit or the voltage of the source, and that's going to be the resistance of the whole circuit as well. So the voltage of our source, we got 8 volts divided by my 14 ohms. I don't know what that is in my head, so calculate, and I get 0.57 amps. So that's the current that flows through the whole circuit. Okay, cool. Now, what's I5? Bella? She got it. Yeah. Remember, the rule for series is that the currents are the same in all places. So the current that flows through the whole circuit, 0.57 amps, guess what? I5, 0.57 amps, and I9 is 0.57 amps. There we go. Same current that flows through all pieces of a series circuit. All right, good. Now, the voltage. Can I assume the voltage 5 is 8 volts?
No.
Good to go?
It's a part of the total.
Yeah, girl. At a last minute addition to our student list.
I think they had it written. Like, why do you do that?
What? Like in some aspects, yeah. Definitely.
I'm not saying not. See, just overall, it is hard to basketball.
It also
clear.
Okay, he's not understanding. He says, basketball takes more better.
Wait, was he her last minute?
He
Okay.
basically thinks
So last thing, the voltage. So I cannot assume that the voltage on this is 8 because we already know that the voltage of the source has to be equal to the individual voltage drops all added together. So these two, although they would add to equal H, that means that both of these have to be less than H, right? All right, so we're gonna have to use our Ohm's law equation again, solve for V. The V equals I times R, but this time I'm solving for the voltage on one specific small piece, just the 5 ohm resistor. So I already know I5, 0.57 amps, times my resistance is 5 ohms. And what do we get? Let's see, 0.57 times 5 gives me 2.85, so 2.9. 2.9 volts. There we go.
I think the resistance is 5
Because I'm looking at just the 5 ohm resistor now. Because it's the voltage, what is the voltage drop across just that piece? Yeah. Alright, so then I'm going to do the same thing. So 0.57 amps times my 9 ohm resistor. Okay, and what do we get there? 0.57 times 9 gives me 5.1. 5.1, not amps, volts. There we go.
That's your fault.
Alright, well let's check. Does V5 plus V9 equal 8 volts?
Yes.
Sure does. So we've done it right.
Heck yeah.
Okay, so that's how we're going to approach a series circuit where we've got multiple resistors in a series connection. Alright. But wait, there's more. What about parallel? That's the other way. Right. If you need to, go ahead and take a picture before I erase it.
I have a picture of you. It's so
you got on
funny.
the video?
Yeah.
Alright.
Not.
If it's not, yeah, you can share if you missed that picture.
Have you been posting, Martin?
Yeah.
I've been getting no notifications.
I posted last
Okay,
class, last class, and
I've been
So
getting
now
no
let's talk about
notifications.
parallel circuit.
I've been like, oh, okay, Corey.
Once again, we're going to start off with our simple circuit here. And I'm going to add another resistor in parallel. Now this means that I'm adding another loop, just like I added the voltmeter to the already formed circuit by adding it to both sides of the item. I'm going to add another resistor in parallel. I'm going to hit it before, and I'm going to hit it after. Look at that, boom! I've got multiple loops here. That is a parallel connection. And let's just do one more just for kicks. Here we go. Boom. And boom. So we've got R1, R2, and R3. Here we go.
that was terrible.
And this is a parallel circuit. One R, two L's, and then a third L. All right, here we go. So let's talk about currents. So here's my current total flowing out of the battery. I'm going to measure it before the first junction, but now, we've got junctions. We talked about that last class. Remember, the current has to split, but we can't lose any, right? We can't lose any. So some of the current goes down here. I'm going to call that I1. And then the rest of it continues on until it splits again. Some of the current goes through R2. Let's call it I2. And then the rest goes through R3. All right, so let's take a look at our rules now. Again, we're going to have a rule for current, voltage, and resistance. So for a parallel circuit, I cannot assume that these are all the same. right? Because the I total has to be equal to the sum of the individual currents through the branches. So I is equal to I1 plus I2 plus however many we have. Now the voltage. It is convenient that in order to measure the voltage, we connect it in parallel because in a parallel circuit, the voltages are all the same in a parallel circuit. So the voltage of the source is going to be equal to the voltage on 1, is equal to the voltage on 2, is equal to however many voltages that we have. Okay, so in a series circuit, the currents were all the same, regardless of in our circuit, wherever that we are. In a parallel circuit, the voltages are all the same. It doesn't matter which one we choose, all right? Now, you might be like, okay, how are we going to add things differently, okay? Well, I don't know who came up with this, but it works. And I call this the inverse sum equation. So it's 1 over the resistance total in a parallel circuit is equal to, and then it's just, we add up the inverses of all of the resistors. So 1 over R1 plus 1 over R2, and however many we have. All right, again, just like it shows on our equation sheet, verbatim, okay, these are our 3 rules for the parallel circuit. All right, so now let's use them. Let's go back to our example problem. I want to use the same exact numbers so we can compare. All right, so I've got an 8-volt battery, and we've got a 5 ohm resistor, and we've got a 9 ohm resistor in parallel with each other. Because again, there's multiple loops. This is not a series circuit, it's a parallel circuit. All right, so the things that we're going to solve for, once again, I'm going to solve for what's the total resistance of my parallel circuit?
14.
What's the total amount of current that flows through it? What's the current that flows through the 5 and the current that flows through the 9? And what are the voltage drops across the 5 and the 9, respectively?
Those are the same.
So, is there something that I already know without doing any math? Affirmative, talk to me.
You know that the total resistance is 14.
Oh, no.
No, it's not.
I definitely have to do math for that. So let's come back to that. Okay. There is something based on our rules that I already know about that I can fill in from my list. Jordan?
The voltage is 8 throughout everything.
Yeah. The voltage is 8 volts in every place on the circuit. Yeah, so V5, that's 8 volts. V9, also 8 volts. There we go. Because the voltages are the same in all parts of a parallel circuit. All right, now let's go back and tackle our total resistance equation. Remember, this is a parallel circuit now, so I have to add them together using my weird inverse sum equation. Let me show you how it works. All right, so we got our 1 over Rp is equal to 1 over 5 plus 1 over 9. Okay, well, I can't do that in my head. I'm just going to use my calculator. All right, so 1 divided by 5 plus 1 divided by 9 gives me 0.31. Now that's not my answer, okay? That's 1 over my answer. All right, so I'm gonna have to invert both sides so that my so that the actual answer is gonna be 1 divided by 0.31. I can't leave it like that. I gotta calculate what that means. Now I'm gonna go back, and in my calculator, I'm going to do 1 divided by my answer, okay? Because I rounded that, but I don't want to round before I actually calculate. So 1 over my answer, and now I can round at the 3.2. All right. Whoa, hold the phone. Now in the series circuit, when I added my resistors together, what did I get?
Same.
Remember the rule for adding resistors in series, we just
resistors.
straight up add them together, right? So what was it before? It was 9 plus 5. What's 9 plus 5?
14.
14, yeah. So before, it was 14. When I connected the resistors in series, it gave me a larger resistance for the whole circuit. But here, when I connect these resistors in parallel, I get a smaller resistance than any of the other ones that form it. It's kind of weird, but true. That's how it is. So if I combine resistors in parallel, the total resistance of the circuit actually is less. As I add them in series, the total resistance actually becomes more, based on how we combine them. All right, good. Well, let's continue. Solve for I, the current in the whole circuit. Remember, I'm going to use my Ohm's law equation again. I equals V over R as I do my algebra. My voltage for my whole is going to be 8 volts here. The resistance for the whole circuit, I just calculated as 3.2. All right, back to my calculator because I can't do that in my head. 8 divided by 3.2, 2.5. Oh, wow, you guys are quick. 2.5 amps. Huh. I think that's more than the current than we got the first time, right? Because for the first circuit, we had a larger resistance, 14 ohms, and we had a current of 0.57 amps. But here we've got smaller resistance and more current. Does that make sense?
Yeah.
Yeah, because remember, the current and the resistance are inversely related. So if I connect my pieces of the circuit in a different way, that allows it to have a smaller resistance with the same voltage, I'm gonna get more current out of it, or in it rather. Cool. All right, can I assume I5 is 2.52?
No.
No. I gotta calculate, all right? So I'm gonna calculate, and we're going to, well, I still use my I equals V over R, but now I'm doing it for the small pieces. So I did it for the circuit as a whole, and I can also use it for the small pieces individually, okay? Now, the voltage is still 8 volts, because V5 is 8, and my resistance is, well, 5 ohms, okay? And I can do that, that's like 1.6, right?
Yeah.
Check my math. Yeah, so I5, 1.6 amps, and then I do the same thing with my 9, okay? I equals V over R, 8 volts because V9 is 8, divided by my 9 ohms, that's my resistance. 8 ninths, like 0.89 or something like that? I don't know. Yeah, 0.89. 0.89 amps. And I bet you if we add those two together, we're going to get 2.5, or definitely close to 2.5, because technically we rounded. Well, that's not rounded, but this is rounded. So, but it's close enough. If I add I5 and I9, I should get close to 2.5. Yeah. And with rounding, it'll make sense. Done. Yes. Alrighty guys, so just a reminder, your pods and your quiz for today are not on what we just talked about. They're only on the simple Ohm's law and the resistivity equation. This is going to be a part of next class's quiz. Next class, we will learn how to go deeper here, because we'll talk about combination series and parallel circuits, as well as something called internal resistance from the battery. So a lot of more complex stuff that is on tap for next class. All right. If you took class notes, I'll check those real quick, and then we're going to start packing up.